Just read the name, sorry, get it. Matthias Beranek is talking about, as said, e-motors and e-mobility market trends and what are innovations in the manufacturing.
Yeah, thank you very much. Hello, everyone. I have the honor to speak directly after lunch, so I hope nobody's falling asleep. I have a fast-paced presentation, so I try to show you as much as possible on what we do and what's state of the art and so on, a little bit about the trends. So for those who don't know TRUMPF, we're like a family-owned business. We do laser technology. It's all about the lasers. We're in the main markets, etc. Our HQ is nearby Stuttgart. That's all the facilities where we make the lasers and do some of the machines. And like our main areas is like machine tools for sheet metal, the laser technology, which is in the biggest chunk in automotive, and semiconductor laser. And maybe some of you guys have heard about that, what's being called the EUV laser. This is the one going to the Dutch company ASML, which is used for producing the latest generation or the future generation of microchips. And this is our former CTO here, Mr. Leibinger, who's one of the families running the company. And he was stating that without this laser, Moore's law would have come to an end, which has a big economical impact, and is certainly a technology that, if you have it in your hands, also raises interest from politics, etc., etc. And that's why if you walk the Brandenburg Gate, there is one TRUMPF flag flying over, and this is certainly not an office for selling lasers, but to talk to the guys who are interested in that technology. Yeah, and that's basically our operational mode. So we do lasers, we don't do the machines. Yeah, so in that case, it's ASML. And in the case of the automotive applications, it's usually some machine or line builders which just take our system as a core component in order to do something which wouldn't be able or wouldn't be possible in any other way. At the moment, we're focusing pretty hard on everything which is somewhat related to artificial intelligence. Most of the time in order to improve our systems, to make it run much better. I will show you one of the examples later on. So this is like high-performance computing. We work with some of the masterminds which are there in the AI. So, for example, Dr. Hochreiter was one of the guys who actually gave ChatGPT the core programming stuff and got no money for it. I think he's pretty much upset about that, but he's still working at advancing his stuff. And so we have collaborations with those guys. In the cars, lasers have played a role for the better time of the last 20 years. So there's obviously a lot of applications in the car body. This is like welding doors. This is cutting of B-pillars, where there's only the laser cutting available. And of course, we do dedicate to e-mobility. That's why there's a lot of applications in the joining and contacting of the battery packs, and even more specifically in the electrified powertrain. So battery manufacturing all the way, fuel cells, and you can think of all of the components which belong to a drivetrain, including, of course, the electric motor. I brought you two examples, just that you see something different than an e-drive. That case, this is a cooling plate for a battery. So that goes under floor. And what needs to be done there is actually to have a liquid tight welding for a few 10 or a few 100 meters of seam length. And for that, we have developed a new technology. So usually we refine what's already existing industrialized laser systems to take over a new application, a new topic. So in that case, it's liquid tight welding with a special sort of laser beam arrangements. And then, while we're at it, we also used that and carried it over to, for example, power electronics housings. So I don't know who's familiar with welding in here, but so die cast welding is one of the most difficult things because it generates a lot of porosities. And we successfully carried over that technology to seal off like inverters or BMSs in order to actually get gas tight, because that's a specification we got. We dealt with it, and so we can apply this technology to different applications. Inside of the battery processing chain, there is literally not a single processing step where there cannot be a laser application, whether it's cutting, structuring, most of the time it's sort of contacting. So I just brought 3 examples which are quite common. So on the upper side, you see the cell contacting. That means, for example, the jelly rolls of round cell batteries are being connected to the outer conducting parts. We've developed special lasers for that. They're actually green, so you can see that. And that has to do with the susceptibility of the copper material towards green laser light, so it takes in the green light more efficiently than any other high power laser light. Then the busbar contacting, this is very popular for each type of the battery cells, whether it's round, prismatic, or pouch. There is always bus bars also on each level of the battery build. And you can see that this is being done with like so-called scanning optics. What's nice a little bit, in many cases we can just trick the materials when using the laser. So welding copper to aluminum is quite a common thing to do there. It's working quite well. And this is due to the specific arrangement of the laser. And here you have to look very closely. This is the next generation of prismatic cell housing welding. This is a very, very popular application. And you can see that the next generation of that will be 3 times as fast as it is today. So very quick. Looking into the EL, we have also different sorts of applications. You can see that on the bigger part of the picture, there's a lot of steel examples. I just want to point out that with the laser, you can have welds to steels which are not exactly weldable, at least to a more common definition. And with the high concentration of power of the laser beam, in many cases we have a certain possibility and processing window to connect even difficult to weld steel grades. And for example, the differential is one of the parts which has been laser welded since 20 years or so. There's a very high experience for that, so you just have to go for it. Also very close to the E-drive then is of course the inverters. And there is an increasing interest in removing, the bolted connections by a laser welded connection. All right, and then we have the E-drive. This is what I'm talking about in depth today, where there is, well, mainly for us it's the hairpin technology, because that's been used by literally anyone now, at least for the larger productions. And the main application is of course here the welding of the open ends, hairpin welding, and also the decoding, that is welding preparation, you can say. The connection of the phase connectors or bus bars, and you also see that here a little bit. Also the stator cores are being laser welded. That most of the time being done in like tier 2 or tier 3 suppliers somewhere, but they also could or would be using lasers. All right, for those who don't know, I will very quickly take you through the processing chain. You can see it's rather long. The laser is here, so the crown welding and the contacting. And This, unfortunately, is a point where the product value is already quite high in terms of value add. So we are most of the time not really allowed to have any failures. At the same time, we have a very, very high number of connections. So if I think 10 years back, there was one part, one laser weld, everything was fine. If one part was bad, you just threw it away. That has long been gone. And that's what we've been dealing with for the last 10 years, you can say. Right. First step is the forming, so-called forming. So that is all which leads to actually having the U-pin. What you could see here is like a sequential machine. Right now, we are capable, or in that case, the Barfuse company is capable of producing 1 pin per second. That's the cycle time of those machines right now, which includes already that laser decoding operation that was not seen in this video, but it's there. Then you prepare the stator core, so you put in the isolation paper, then you arrange the U-pins to put it by the means of grippers into the stator core. And then you have the two processes, one of which is the so-called widening, and then the other one is the so-called twisting to have that distinctly twisted crown on the upper side. And then I just skipped the laser welding for a moment. So after laser welding, there's only a very few steps left. All of them have to do with isolation, either of the welded open ends or the trickling and isolation of the whole slots. Both of them are working with inductive preheating, so you heat up the part, you apply the isolation layers, in that case liquid. In that case, it's like powder dipping, and this is how you go to your isolation, and after that, there will always be some sort of end-of-line testing. All right. Yeah, I mentioned already, the part is very expensive once arriving at the welding station. That's why it's not only a laser which is used there. It's a whole system with a lot of sensors. So we got the laser beam source supplying the light for the welding. We have scanning optics. And then there's a whole battalion of sensors. In any case, I will show you the positioning sensors and also the OCT, and also how we apply the AI and some of the adaptive processing. Like said, the laser system, as just shown on the previous slide, is closed. So it's capable of running autonomously, more or less. What we need is like only a start-stop from any sort of machine who is supposed to weld that stuff. And this pretty much keeps the system open to a lot of machine building companies who are capable of supplying production lines. And this is why we scaled so quickly, especially in Europe. And that's also why we can adapt to new sorts of motor designs, like the axial flux motor, for example. Got an example later on for that. Yeah, and all of those companies have done several projects already. Still, the biggest player, at least in the European, is certainly the Grove company. They are very famous for producing hairpin stator production lines, and they will use the laser system at one point. Yeah, welding-wise, we have developed approaches and processings for each of the types you can see on this slide. I will show them later in more detail, and most of the time it's just about the adjustments we put, for example, for the parameters, and a little bit for the welding strategies we apply. What's good is that like the specific sort of system we're using would be applicable for all of the shown products. Right, at the moment we have 700 high power laser systems installed worldwide. which means we scored pretty much every project. And that should be somewhere between 3 to 350 production lines already. All right. So just so you've seen one of the contacting, we usually use a strategy which is melting the first pin, then the second pin, and then there is some sort of integral movement over the 2 pins in the end. All of the videos you're seeing when a welding is going on are high-speed videos, so that means in that case this was like a 100 milliseconds weld there. Then you do this 200 times, and then you got a nice little stator ready for putting on the car. The laser is highly controllable, so that's like an example sequence of the weld. So you can see we do some jumping around. We can also control the laser power along the single paths. So the laser light is actually the quickest. We can regulate it within some microseconds because it's a real-time path and the speed of light is obviously very quick. So we can even do fine-tuning like that. Yeah, and to even get deeper in the application, we are going to, that's the synchrotron facility in Hamburg. So that's a particle accelerator. And we pretty much misused it to build a high-speed camera based on X-ray because the particle beam has very high energy, so we can do an X-ray through the parts while doing the welding. So you see how the laser is going in here and how we connect the part. You see how porosity is being formed during the weld and also how the porosity is being removed during the weld. And to get to an understanding which is necessary to do that process properly, you have to see we have to go through quite some lengths at some point. But it's also a lot of fun, so I can tell you that. We have the sensors, which I mentioned. So we have a camera, and camera detection actually was based on some grayscale, edge finding, and so on. We changed it. So our detection is completely based on AI. And just so you've seen actually a welding process going on inside a machine, that's the optics again, with all the sensors in there. That's me. And this is how the thing is being programmed. It's not that interesting, but interesting is we detect all of the pins, either sequentially or all at once. There can be different modes. And this here is showing what's the problem with the standard detection. And we solve it by AI. Here you have how we train the AI, actually. This is by manual labeling in the first place, where we have developed a very good few-shot learning, which means we make 2 or 3 manual trainings, and then the AI can already work on predicting the parts. And then we basically just switch it on, and magically there is no more problem with the detection. And this was basically something we, of course, had to deal with for quite some years in the beginning. So there were always some faulty measurements, stuff like that. It's just about the statistics. If you make millions of detections per day, certainly one of them will go wrong. And we've brought down the failure rate quite dramatically by applying that AI. All right. So then we have a little extension. So we not only do use it for detecting the parts, we also can use it for controlling what has happened, to check on the result. And so what you see here is, of course, a mock-up where we applied different failure modes within the stator and just trained the AI to also detect failures. Because what's possible in the welding station still is that at some occasions we can apply what's called repair strategy, which means that you have the chance again to bring up the yield rate a little bit more, to make a part which otherwise would have to be reworked or something. You can still weld it within the welding station. And so for that, we use the advanced detection here. So that's also a feature which is possible. Right, and then we have optical coherence tomography. So that's now a direct measurement. You also see it's a different sensor. So that's also a laser beam, but it's more or less powerless. It's like a measuring beam. And besides just scanning for geometrical features like height differences or the welding result, you can also measure the weld depth, which has been considered like the holy grail of laser welding, to actually get to this very concrete and good information. That's basically the most information you can get out of a weld. And here you can see it going down. So the welding depth is basically gradually increasing by the time we go on with the welding on those pins. And this is pretty much the first time we get this high degree of information out of one weld. And that's also the point where we can actually go to a 100% quality assurance, because that's running with each and any pin, and that's not possible in today's production. Today's production is sample testing, most of the times using a CT scanner, which allows for only a few parts per hour maybe, and we would be able to detect any weld which is going on. Yeah, and with all that information, we also go into adaptive welding, adaptive processing, which means once we got the information from the camera or even from the OCT, we can still try to apply parameters which are more suitable to a certain situation which can occur, which I've pointed out here. So those are the typical things which can happen in a production environment. And what we do then is to automatically adapt either the strategy or just some parameters of the laser in order to get to acceptable welding result. So you can see that this is the more common case. So if you have very strong deviations in your parts, that's certainly not a good welding result. And on the right side, we've just used the information coming from the pre-measurement indicating that there is a gap, and then we adapted the parameters in a way which are suitable to bridge that gap. And similar can be done for all of the other deviations. And you've seen that's a full 3D compatible measurement mode we could apply. So we got all the information even before we start to weld one of those pins. Then for the trends, what's actually very common, of course, is the U-pin. So pretty much every OEM has some sort of U-pin stator on the products. What we do see, especially in China, is the so-called X-pin and mini-pin. Those two concepts are basically targeting to reduce material use because the pins are cut shorter, which also means that the head height is reduced. The state of these applications is basically for the mini pin that has a good feasibility, where your processing window gets a little bit smaller for the contacting, but it's very handleable. With the X pin, and what I see, the yield is catastrophic. So that concept is certainly not really ready to go to a full-scale production. It's very hard to adjust the single processing steps to the demands of that. So at the moment, it's quite hard to get to a good output. For the mini pin, I will give a little bit credit to the Schaeffler company. They have shown one of their products at the IAA, which was a few weeks ago, and I'd like to see that. You can see the welds are pretty localized. So for sure, if the pins are shorter, we can only put in a certain amount of energy which fits to the volume we want to create. So here in that case, there is no welding pearl as we've seen in the other examples. We have produced aluminum winding stators, and I'm pretty sure, or at least I hope, at the next conference we can talk already about serial products. I have high hopes. I do see the projects. Of course, smaller scale and so on. But obviously, it's an attractive alternative when the use case is right. Okay. And the last thing I want to talk about, just because we've just had some very nice records with that, is axial flux motors. All of that stuff is all around the internet, so I just made some screenshots. Axial flux motors are a little bit different in terms of the workflow of the processing chain we have. We did some adaptations connecting-wise, or for what the lasers have to do. It's not that tricky. We can deal with that. There are quite some smaller differences. So on the right side, I pointed out the processing chain for the axial flux motor. We do see changes in how the coils in that case are manufactured, and the contacting is just a little bit different. So I give you an idea about that. So for the forming, instead of U-pins, we have to create the coils. And then the finalized coils are assembled to the cores, and then the decoding is happening. So the order of how you do things is just a little bit changed in that case. And in the welding, it depends on how the design of the axial flux motor actually is. So if we have different orientations of the open ends, it is certainly that you have to have something which can manipulate the part, so the stator in that case, in order to reach the let's say the pins or the connections. Also the phase connectors, they're usually put on the outside of the stator, as well as the terminals. Yeah? So you have to have like 2 or maybe 3 different poses in order to finalize the welds. The good thing I see is usually that there's less connections compared to the U-pin stator. So we have concepts for that, and you can imagine at some point we will see a serial product quite soon. Another example is actually a wave-wound axial flux motor, which I had in the lab just some days ago, which is from a university, but that case, you can see the orientation of the connection points is just that you can work only from the upper side. So there is no reorientation necessary. The welds are pretty straightforward. And here you can also see how we connected the terminals. So if you do the design, let's say a little bit different, and let's say production orientated, also the axial flux motors can be straightforward. Right? That's pretty much it. So what I've shown you is that there is nothing in e-mobility which is without the laser. That for the hairpin motors, we have established concepts. We just have to do it. And yeah, that most of the technologies are specialized or tailored to the application. And you've seen that AI is coming, of course, data sourcing, quality data storage, that all of that is increasingly demanded. So that's what we're dealing with. And if you want to try, because usually the laser is a little bit more expensive in terms of invest, we offer to try everything. So you can see that in each main market we have at least one lab where we usually go for feasibility testing or testing of one of those sensors, which are also crazy expensive in most of the cases, just to make sure it fits for the application intended. All right, That's it. Thank you very much. Questions, please.
Okay, thank you. Also, good application of AI as terms of a professor. I like it more to see AI applied here than in writing of bachelor theses.
Yeah.
But questions from your side?
Hello. Thank you for a very nice presentation. I have a question about you mentioned that we can have in the depth of the weld with your newer applications. Is it something that is already in production units that you have or solutions that you already provide, or is it an R&D in the R&D phase, or it will be rolled out in the future?
The weld depth measurement is already provided.
Thank you.
The recommendation for the manufacturers is to get used to the output. You have seen that a very nice curve. And at the moment, we're working a lot on how to, about the interpretation of that curve. So how does it actually fit to the output or to the target value, which is usually a certain volume. So we have a one-dimensional result and want to project it to a three-dimensional result. But very high hopes, correlation is there already, it's available.
Thank you.
Thank you also for the presentation. I have a follow-up question to what the gentleman asked. So in terms of the weld depth measurement, is it possible to also measure the weld depth at the interface of the two mating parts during the operation, and then make some statistical analysis of if you produce thousands of units per day, how this weld depth or the depth at the interface is varying according to time or something like that. So basically your laser can scan and measure the depth at each point, or let's say at some distance from the from where the laser starts or from the weld starts.
Yeah, correct. So you have to imagine it pretty much being in the same position as the actual laser welding beam. So the moment you start like boring, penetrating into the material, the measurement is following that. That's why you see that gradual.
Okay, so it's done in
change.
parallel to the operation, let's say. Simultaneously, you
Correct.
also... Okay.
Correct.
Okay.
Yeah.
Very interesting.
So you see one-on-one what's happening.
Okay. Thank you. And maybe one more question. If there is already an existing facility for laser welding, can this be retrofitted, or just the measurement part?
Depends. Depends, usually goes with the most recent generation of optics. A lot of installation have the previous optics, so that's often discussed, but theoretically it's retrofittable, yeah.
Okay, thank you.
Yeah.
Okay, then final question.
Hi.
Hi.
Really lovely presentation. You talked a lot about, I call it traditional hairpins with nice big long weld targets.
Yeah.
And then you mentioned briefly the lovely Schaeffler mini pin and X-pin concepts as being kind of hard.
Yeah.
I imagine they changed the game completely, really, with having a tiny amount of target that you can melt. Can you talk a bit about how you're going to solve those challenges?
How do you mean?
As I see it, you've got a traditional pin.
That's understood.
And you've got loads of material that you can
Yeah.
melt and form and flow
Yeah,
and
yeah.
manage. Whereas with X pins and mini pins, you've only got the top. You haven't really got any spare material to weld and flow.
That's correct. And
So how do you do it?
that's like, yeah. So physics is if you recalculate it and want to achieve a certain connected volume, which is the typical case, there is a minimum energy amount you have to put into those copper volumes in order to generate that. And you cannot undercut that because that would be magic, some sort of. And what they do with the mini pins and also with the X pin is to restrict what we even can put in energy, just for the sake, it's my personal opinion, just for the sake of saving material and height of the materials. Also, they shorten like the decoded length, which burns down all your insulation and stuff like that. So we usually do tune down the energy put even further, which then in some cases might even undercut what we basically wanted as a connected area. And usually, or luckily, it's not really up to me to say if this is good or bad. I can do it, and it needs to be checked for the product, really. Because we come from a point where we say our industry standard is to connect 120% relative to the wire section, is where we are safe, even if there is like production variation, stuff like that, right? And now if you intentionally go to 100%, 90%, 80% connected area, question needs to be answered. What's for the connected area? Like what's for the conductivity? And how fast do we undercut that even? So there's a lot of question marks to that. We're working on it, but it's definitely more challenging than, let's say, the regular stuff we're doing.
Okay, thank you very much for this interesting presentation.